Okay. Good morning, everybody. I'm Kedar Damle from the Tata Institute, and I've emerged from the woodwork to chair the last session. And we have Subroto Mukerjee, who's going to tell us about the phases of hardcore bosons or bosons on frustrated lattices and interesting phase transitions in them.
Well, thank you very much. I'd like to thank the organizers for making me a part of this extremely illustrious lineup. So thank you very much, Arindam and Krishnendu. I don't see either of them here, but thanks anyway. So as the organizers mentioned yesterday, at least one of them, that there is a belief among a certain section of people around the world that the world is going to end today. And I'm hoping that that doesn't happen, not the least because I hope that mine is not going to be one of the last talks you'll ever hear in your life. So let's hope we make it through the day and further. I'm going to talk to you today about phases and phase transitions of bosons on frustrated lattices. So right at the outset, let me make it clear that this is quite different from the main theme of this meeting. So this doesn't have anything really to do with graphene or topological phases or Majorana fermions. What I'll be telling you about is a phase of matter that's a lot more conventional. That's something which can be described in terms of standard order parameters and not topological quantum numbers. I do have some interest in things which are topological, and in case you're interested, there's a poster on work on 1D systems of bosons where you can realize Haldane type phases. I think it's poster number 2. So if you're interested, please go and take a look at that. But what I'll be talking to you about today is phases and phase transitions of bosons on frustrated lattices. This is work that's been done along with these collaborators, and I'm going to talk about the published part of the work. So there's a paper that's been published already and another that's on the archive, and I'd like to thank the Department of Science and Technology, Government of India, for support. Okay. So let's start with something which I'm sure most of you are familiar with, but it doesn't hurt to go over it again. So suppose we look at interacting bosons on a lattice and ask what sort of phases emerge. So the standard model for doing that is this thing called the Bose-Hubbard model, which is not very different from the Fermi-Hubbard model, which has been mentioned a few times in this meeting. The main difference, of course, is that instead of fermions, we have bosons. So there is some lattice on which there are bosons which can hop, and I've taken the hopping to just be nearest neighbor here, but you can have a more general kind of hopping, and there is an on-site repulsive interaction between the bosons. So this is in some sense the canonical Hamiltonian to study interacting bosons on a lattice, and it's been studied using a variety of techniques. And the phase diagram for this model, at least, is reasonably well known. This is what it looks like. And the most important thing is that in addition to having a superfluid phase, you also have these Mott insulating phases, which occur at commensurate values of the density. And if you want a cartoon picture for what the superfluid and the Mott insulator are, so this is a good cartoon picture. So the picture is that in the superfluid, the bosons are mobile. They can hop around. And the physics of this is really dominated by the hopping term. But on the other hand, when the interaction gets sufficiently big and you are at commensurate filling, what happens is that the bosons basically, so let's assume that you have one boson per site on an average. So what happens is that the bosons are frozen at lattice sites simply because the strong repulsive interaction strongly discourages any hopping, any movement of the bosons. Okay, and so this is something, so these two phases have been seen in experiments. About 10 years ago, there was this experiment done on cold atoms where this particular kind of model was realized, and it really sort of jump-started this field of looking at correlated physics in cold atoms. And what you can see is that, so in the experiment, they looked at the momentum distribution of the bosons, and in the superfluid phase, you have these strong peaks at essentially at zero momentum, but with these umklapp peaks, which tell you that there's a superfluid in your system. And then, as the interaction was turned up, the peaks started getting blurry and eventually disappeared, which was indicative of the Mott phase setting in. Experiments on realizing the same model on solid-state systems had been done earlier on Josephson junction arrays, where the diagnostic of choice to look at these phases was transport. And so this is really resistance as a function of temperature in these Josephson junction array systems for different values of what in our language would be the ratio of the interaction strength to the hopping strength. And it turns out that you have both sort of a superconducting phase where you have zero resistance at finite temperature, assuming that the parameters have the right ratio, and then you also have an insulating phase, and you have a phase transition between them.
This part is not clear whether bosonic picture applies or not.
Right,
I mean,
right.
It's still
Right. No, I agree with you. I agree with
and
you.
that might be an Anderson insulator rather than a Mott
Right, right. That
so
was
motivation is fine.
right. Exactly. So I'm not going to say anything more about this aside from
I was
this.
just making sure we agree that.
No, I do. I have no complaint with that. Okay. So, so what I'm going to talk to you about today is the effect of frustration on a system like this. So let's just quickly look at what we mean by frustration. So the standard example of frustration is, standard textbook example of frustration is presented mostly in the language of spin systems. So imagine that you have some kind of a triangular lattice, and let's say at every lattice site you have an Ising spin. So this is a completely classical system. You have spins that can either point up or point down along some particular direction. And let's assume that the interaction between neighboring spins is antiferromagnetic, so something which wants to align the spins in opposite directions. So if you have a triangular plaquette like this, and if you know that this spin is up, the antiferromagnetic interaction here would ask this spin to be down. But then if you look at this spin is confused. It doesn't know whether to be up or down because it's neighboring both the up spin and the down spin. Okay? So what happens then is that when you have frustration of this sort, it gets in the way of ordering. And that often gives you very interesting physics. So one thing which could happen, which in fact happens for this triangular lattice Ising model, is that you can have many classical ground states, something which scales with the system size. And then what happens typically is if you want to somehow pick an ordered state, either you need more degrees of freedom, so you have to go beyond Ising states, or you have to put in quantum mechanics. And then when you put in quantum mechanics, especially in frustrated systems, you can actually get very interesting states like spin liquids, for instance, which again I'll not say very much about, except to say that these such quantum frustrated systems are believed to be existent in nature, and these are examples of compounds where this kind of physics is believed to be operative. There are people in this audience who have worked extensively on some of these systems, so I won't embarrass myself by saying any more about them other than just showing. Who is Herbert Smith? Herbert Smith, I believe, was a mineralogist who went exploring different places in South America in search of exotic minerals, and then came across this. I don't think his motivation for looking for what's called Herbert Smith right now was that it's a Kagome lattice. I forget what the original.
He was not interested in spin liquids?
I don't think so. Right.
I'm so disappointed.
Right. But he seemed to have a nice explorer's name, Herbert Smith. Right. So I don't know what his motivation was for finding this particular compound interesting.
He was a crazy mineralogist who was looking for new rocks and new minerals all over the world.
Right.
And he didn't name it Herbert Smith.
Right.
He discovered many things, and this is one of the things.
Right. Okay.
I asked how long when, that's why.
I see.
What is this Herbert Smith?
Okay. So, all right. So I gave you the motivation for frustration in terms of spins, but we are interested in a bosonic system. So how do you make a bosonic system frustrated? What does it even mean to make a bosonic system frustrated? So let me answer the first question. How do you make a bosonic system frustrated? Well, the way you do it is by, so imagine again that you have some lattice in which you have this model defined, and this, let's say, a square lattice, and you have plaquettes, and the way you make the bosonic system frustrated is by threading flux through the plaquette. If the bosons were charged, you could actually think of this as electromagnetic flux, and if they're not, then you can still think of it as some flux which goes into the hopping through a Piles factor. And it turns out that this kind of thing, at least the single particle physics of this, was studied, and some beautiful results were found as far back as 1976 as the famous Hofstadter butterfly, which I think many of you are aware of, which really deals with a system like this. But for us, what's important is that when you have rational flux like this of the form P divided by Q, you end up with Q bands with degenerate minima. So now, if you're trying to, if you have bosons in a system like this, and bosons like to condense at minima, then they have, a very large choice of possible minima, Q bands, and that sort of introduces the frustration. The bosons really don't know where to go and condense. So this is called kinetic frustration, because the frustration is really coming from the hopping, the kinetic energy in this Hamiltonian. And then if you have a system like this, it's natural to expect that the interaction term would help in resolving this frustration. So the question then is that when you have a phase diagram like this with frustration of this sort and interactions, when you have a Hamiltonian like that, what would the phase diagram be? So incidentally, in case you're still not convinced that the bosons would be frustrated in a system like this, here's another way to look at it. So imagine that this flux, the flux quantum that I had was 1/2. So this is what's called a fully frustrated model, and I'll be talking about models of this sort. So just consider a single plaquette. Now imagine that you're looking at some condensed state of the bosons, so which means that I can think of basically an expectation value of the annihilation operator in that state, which is an order parameter. And let me assume again, for the sake of simplicity and for illustrative purposes, that the amplitude of the order parameter is constant across the system. So this doesn't have any dependence on lattice side, but it's the phase here that can depend on where you are, and that's important. So if you look at the hopping term really is going to go as the cosine of the phase difference between the two sides that are involved in the hopping. And now if you look at a square plaquette, one particular way to realize the sort of half flux quantum is to say that the hopping along this side and this side have different signs. So it's minus t here and plus t here, and these are both some minus t perp and minus t perp. So these are the same, but these have opposite sign. So now imagine that you have phase equal to 0 at this side. The minus t bond here would also like the phase to be 0 here to minimize the energy. And similarly, the minus t perp here would like the phase to be 0 at this site as well. But now this site is confused about whether to be 0 or pi, because this bond would want to make it 0 if this one was 0. But this bond, because it's plus t, would want to make it pi because this phase is equal to 0. So this is another way of looking at frustration, that frustration really manifests itself as a frustration of the phase of the order parameter. So again, why is this interesting? Why would you care about frustrated bosonic systems? So again, it turns out that there's a classical analog of this which has been studied theoretically, and it is simply the classical XY model on a square lattice. And again, you can frustrate the classical XY model on a square lattice by threading flux in this way. Or what you could do is you could look at the classical XY model with antiferromagnetic interactions on a triangular lattice, where the triangular geometry already sort of makes it frustrated. And this is something which was studied quite some time ago, and I believe that all through the 80s there's a lot of confusion about what the phase diagram of this was and what phase transitions there were. But I think, at least for the square lattice problem, the fully frustrated square lattice problem, it is now believed that there are two phase transitions, and so one of them is a Kostelis-Thouless type phase transition. The other one is an Ising phase transition, and the Ising order in this XY model comes because of the frustration. And what I'll be talking to you about is actually going to be a quantum analog of that. And again, if you think of Josephson junction arrays as motivation for this kind of studying this kind of physics, it turns out that people have also looked at frustrated Josephson junction arrays experimentally. So this was sort of the data that I showed you earlier. This is on a similar system of Josephson junction arrays, but with a frustrating flux, making it fully frustrated. And it turns out that one of the things which happens when you put in frustration is that the effective U for the Mott transition gets reduced, in the sense that it's now easier to drive the system out of the superfluid state because the frustration is helping you do it. The frustration is sort of trying to kill the superfluid itself. But more recently, it turns out that in experiments on optical lattices, it has actually become possible to make optical lattices in geometries like the triangular geometry, or even in a square geometry, it has been possible to thread flux through the plaquettes. And what people have seen experimentally, so these are all experimental papers, is that this, the geometry or the flux that you thread through the lattice gives you superfluid phases with additional order aside from just the regular superfluid order, and that's manifested by, well, here at least that can be seen if you look at this closely and think about it, from the fact that you have an appearance of peaks in the boson distribution at values other than k equal to 0. So this is indicative of the presence of more than just one minimum. You have several minima, and you have peaks corresponding to all these minima. Here in this experiment, they actually were able to look at the phase of the superfluid order parameter in this triangular lattice geometry, and depending on how they adjusted the strengths and the signs of the couplings, they could actually get phases which were ferromagnetic and spiral and rhombic and so on. So what I'm trying to tell you is that people have been studying frustration in bosonic systems, and they have been able to realize it experimentally and have studied superfluid phases recently with frustration. So the question that we're asking is what happens when you also have interaction. So the frustration does something to the superfluid, but presumably the interactions would also do something, which the interactions would normally try to drive it into a Mott insulator. So what happens when both these are present at the same time? So the particular system that we've studied is actually a one-dimensional ladder system. So this is a ladder where you have two legs, and you have these plaquettes, and these plaquettes are fully frustrated. So you can think of a pi flux threading each of these plaquettes. So a Hamiltonian for a system like this looks like this. So you have minus t hopping along one of the legs and plus t hopping along the other leg. So this is what realizes for you this frustration. This is incidentally a particular gate choice. You could have chosen some other combination of hoppings which would have given you the same frustration. And then you have an on-site interaction at every site on both these legs. So basically you have two legs, frustration in the plaquettes, and of course hopping along each of these rungs, and an on-site interaction. So this is like a Bose-Hubbard model for a 1D ladder, but with frustration. And I'm going to look at the case of one boson per site at commensurate filling so that there is a Mott phase. And so the question is, what would be the phase diagram of something like this? So one way of understanding what the phase diagram would be to first switch off the interaction. So let's say you set u equal to 0 in this Hamiltonian, and then it's just a tight binding model problem. If you also set t perpendicular equal to 0, meaning that there's no coupling between the legs, and the fact that you have an opposite sign of hopping along the two legs would give you a band structure like this. You'd have one band coming from, say, this one coming from the lower leg and this one coming from the upper leg. So this is when you have neither interactions nor hopping along the rungs. Now let's say you switch on hopping along the rungs, a small value of hopping, let's say, and what you'll see is that a gap will develop at these degenerate points, and you will get two bands which look like this. So now you can see that you actually have two minima in this band structure. So there's one at k equal to 0, and there's another one at k equal to pi. So if you wanted to put bosons in this and get them to condense, form a single particle condensate, then the most general single particle condensate wave function would be some linear combination of 0 and pi. So one thing which I'd like you to notice is that the character of the minima are different, in the sense that this minimum is really coming from this band which corresponds to the lower leg, and this minimum at k equal to pi is coming from the band which corresponds to the upper leg. Okay, so there is, at least for small values of t perpendicular, you can associate a particular leg with each of the two minima. Okay, so now let's ask what interactions do. So here you see this frustration that the a0 and a pi could be anything at this point. And the question is, do interactions help in giving you more definite values of a0 and a pi? And it turns out that interactions actually do that. So we have an average density of one boson per site, and we have repulsive interactions. So what the repulsive interactions would like to do is discourage having more than one boson at a particular site. Okay? So then the only way that you could have a single particle condensate in the presence of repulsive interactions is if the modulus of A0 was the same as the modulus of A pi. Or in other words, you had the same average density of bosons along both the legs. Okay, so what interaction does for you is it tells you that these have the same amplitude. So all that you have in this wave function are two phases. So there's the global phase of the wave function, which is a superfluid order parameter, and there's a relative phase between the k equal to 0 and the k equal to pi wave function. So now you can write down some sort of a coherent many-body state coming from the single particle wave function, which would be sort of your condensate wave function. And if you just do a simple Ginzburg-Landau type theory with this sort of, ansatz for the wave function, what you will find is that you will get a Ginzburg-Landau energy which looks like this, and the important so U0 and V0 are just some terms which arise when you go from real space in which the Hamiltonian is defined to momentum space in which the momenta are defined. These are just some coefficients corresponding to that. The important thing is that you have this sort of term here. So the script phi's are basically, think of them as the order parameter for k equal to 0 and k equal to pi. But what you have is that you have this mixing, this coupling term, which is like an Umklapp term between k equal to 0 and k equal to pi. And this is the important term which governs the physics that I just talked about. So if you try to minimize this free energy, what you'll find is that this term favors two things. One is that it favors a relative phase of plus or minus pi by 2. So this relative phase now from energy minimization is constrained to be plus or minus pi by 2. And it also favors this equal amplitude that I told you about just a slide earlier. Okay. So the important thing is that now you have an extra Ising symmetry in the superfluid, which corresponds to this relative phase being plus or minus pi by 2, in addition to the superfluid, the superfluid order which would be present. So and it turns out that the choice of plus or minus pi by 2 corresponds to something physical. So for each choice of the sign, you have a certain pattern of staggered currents along the ladder. So in one case, what you would get is you would get a pattern of, say, clockwise, anti-clockwise, clockwise, anti-clockwise supercurrents. And in the other case, you'll get the same pattern moved over by one lattice constant. Okay, so that corresponds to the plus or minus pi by 2. So the superfluid now has this pattern of currents which are flowing. So, we call it chiral order. So this is a chiral superfluid. And if you ask what symmetry is broken by this, it is U1 cross Z2, U1 because it's a superfluid, and Z2 because you're picking some particular kind of chirality. I should point out that we're talking about a one-dimensional system. So when I say that it breaks U1, what I mean is that you have algebraic long-range order in U1, but this is not a continuous symmetry, so you can actually have continuous long-range, so you can actually have long-range chiral order in the system. And this is what the wave function would look like. So this is a superfluid, okay? And so you can now ask what happens as you increase U. How does this superfluid go into the Mott phase? Okay, so that is the question that I'm asking. So let me just cut to the chase and I'll give you the details. At the important sort of result of this work is that U is increased. You don't go directly into a featureless Mott insulator. In the sense, you don't go into a Mott insulator of the sort whose cartoon I showed you in the first couple of slides. There is an intermediate Mott insulating phase, which is Mott insulating because there's a charge cap, okay, so you can't have any transport, but there is still this pattern of staggered currents in the Mott phase. So there's actually a chiral Mott insulator in the system as U is increased, and then of course as U is increased further, then the chiral Mott insulator disappears and you just go into a regular featureless Mott insulator. So there is this intermediate phase, okay. So I should mention incidentally that this idea of a chiral superfluid is by no means new. People have been looking at frustrated bosonic systems for quite some time. And in fact, the authors of one of these papers, Krishnendu, is sitting right here. And but as far as we know,
actually two more.
Two more, actually, sorry, you're there.
Deep and I are
also on this parallel page.
There's a very long physics.
Right. Sorry. So two of these authors, I'm sorry, are sitting here. But as far as I know, none of these papers talk about the chiral Mott insulator. Okay. So, I gave you the punchline. I told you what the main result is. But suppose you actually wanted to study this more systematically without knowing what the answer is. The way you would now think of looking at the Mott phase. So we have a description of the superfluid phase. One way to look at the Mott phase and the transition between superfluid and Mott is to do single-site mean field theory. And it turns out that when you do single-site mean field theory, you actually do get an expression for a phase boundary. But the important thing is that the single-site mean field theory gives you a direct transition from the chiral superfluid to the featureless Mott insulator. It doesn't tell you about this intermediate chiral Mott insulator. So if you want, and what happens is that the U1 and the Z2 order sort of get unified and destroyed at the same time in the transition. But if you want to see the chiral Mott insulator, then you have to go beyond mean field theory, and the question is, how do you do it? So one analytical way of doing it, which is what we're pursuing at the moment, would be to use bosonization, because after all this is a 1D system, and see if in the language of bosonization you can actually see a flow away from the chiral superfluid into the chiral Mott. So we're in the process of doing that. But what we've already finished doing is actually looking at this numerically. So one idea is that you take this bosonic system and you treat the bosons as rotors, okay? And so then you can think of this as a classical system in terms of the rotor variables in one higher dimension. So it's now a 1 + 1 dimensional system. And you can study that using classical Monte Carlo. The other thing which you can do, which is just simulate the quantum model directly using something like DMRG, because it is, after all, a one-dimensional system. Okay. So we've done both, and so this is what the geometry is for the classical system in one higher dimension. So it's basically just these ladders stacked along some imaginary time axis with these plaquettes, which are perpendicular to the direction of the imaginary time axis, frustrated, and then you have some sort of an XY model on this geometry, with the couplings in the classical model sort of determined by the couplings in the original microscopic Hamiltonian up to some discretization parameter along the imaginary time axis. So you can take a classical system like this and do classical Monte Carlo, which is what we've done. And what we see clearly are two transitions. So one transition is a superfluid transition, which is in the Kosterlitz-Thouless universality class. This is from doing standard numerics to determine such a transition. The other transition is a 2D Ising transition. So there are two distinct transitions, which is in the 2D Ising universality class. Again, standard numerics to determine that. And it turns out that if you now look at the phase diagram in the parameter space of this classical model, you have the chiral superfluid, which is the phase which is both U1 and Z2 order. You have the regular Mott insulator, which is the completely disordered phase. But in between, you have this chiral Mott insulator, which doesn't have any U1 order, but it still has Z2 order because the Ising transition happens after the U1 transition. Sorry? Oh, what are the two axes? So this is J perpendicular, and this is 1 over, so let me just go back to, so the two axes are basically these couplings here. So this particular phase diagram has been obtained for a fixed ratio of, for a fixed value of J parallel, and you have J perpendicular along one axis and 1 over J tau, which you can think of as like temperature in this classical model. Right, it is. Yeah, so I'll show you the quantum phase diagram in a second. So this is the quantum simulation using DMRG. And so once again, we find a Kosterlitz-Thouless transition where the U1 order disappears, and an Ising transition where the Z2 order disappears. And this is, these are again sort of standard numerical ways of detecting these transitions using their scaling properties. So you can also, on the basis of these DMRG calculations, draw a phase diagram in the actual parameter space of the microscopic Hamiltonian, and sure enough, it's U here instead of 1 over J tau, and this is T perpendicular by T. So this is perhaps a more a phase diagram that's easier to understand because it involves the microscopic parameters of the Hamiltonian. So again, you see that you have the chiral superfluid and the Mott insulator, and in between you have this thin sliver of the chiral Mott insulator, which is this phase where you have a charge gap. It's a Mott insulator, but it has this chiral order parameter being non-zero. Okay, fine. So this was all again, numerics and in the language of the different things which go into the order parameter. But is there a more physical picture for what this chiral Mott insulator is? Because for the superfluid and the regular Mott insulator, there are physical pictures. I mean, the simple cartoons, for instance, that I showed you in the first couple of slides. So what could be a physical picture for the chiral Mott insulator? So here's one picture. Again, this is just really very qualitative. We haven't done any calculations. But the idea is that the chiral superfluid is something which you can think of as being, in some sense, like a perfect vortex-anti-vortex crystal. Okay, so you have a sort of a ferromagnetic vortex-anti-vortex crystal. And we know that one way of looking at a regular Mott insulator, I mean, this is probably not the most common way of looking at it, but it is a way of looking at it nevertheless, is that it's a vortex-anti-vortex superfluid. Okay, that when the system is disordered, you can think of these vortices and anti-vortices being completely mobile and disordering the system. So in this language, you can think of the chiral Mott insulator as being like a vortex-anti-vortex supersolid. In the sense that in the chiral superfluid, you have this perfect crystalline pattern of vortex, anti-vortex, and so on. And then you start developing defects, vacancies or interstitials, okay, which are then, mobile and can give you some sort of superfluid order in the vortex, anti-vortex language, but while preserving the background crystallinity of the vortex, anti-vortex pattern, because these are defects, okay. So then one particular picture of this chiral Mott insulator could be as a vortex anti-vortex supersolid. As I told you, this is just very qualitative. We haven't done any quantitative calculations to actually justify this. Something that we've done slightly more sort of quantitative calculations is to think of it as an indirect excitonic condensate. So what does that mean? So if you look at the excitations of the regular Mott insulator, so you have gapped excitations which correspond to double occupancy and zero occupancy. So the cartoon picture of the Mott insulator is you have exactly, how much more time do I have, by the way? 5 minutes, okay, I should be able to finish. Yeah. So one cartoon picture of the Mott insulator is that you have basically, if you have an average of 1 boson per site, you have exactly 1 boson at every site. And now if you're asking about excitations, so you can have gapped excitations where you have double occupancy or zero occupancy. And then once you have created these excitations can move, so you can think of a band structure or a dispersion for the excitations. And that would be semiconductor-like. You would have one band for double occupancy, one band for zero occupancy with a gap between them. And that band structure would not look, in this particular case, very different from this. Okay. So in the presence of frustration, such a band structure would not look very different from what I've drawn here. So in our frustrated case, again, you have a similar situation. So you have gapped particles and gapped holes, and there's some dispersion. Now it turns out that if you can form an indirect excitonic condensate, meaning that you have a case where you have particles and holes, but which are not in the same minimum. So one of them is at k equal to 0 and the other is at k equal to pi. And if that object condenses without the individual excitations condensing, you can show that that would actually give you such a condensed pattern of excitations would actually give you these staggered currents. So this is a Mott phase because you're starting with some sort of a semiconductor-like dispersion for the excitations. But if you happen to condense these particular kind of excitons here, you can show that you can actually get a staggered pattern of currents of the sort that I described. Since I have only 5, maybe 3 or 4 minutes at this point, I'll just go over this very quickly. It turns out that you can also sort of write down a variational wave function for this chiral Mott state, which starts with writing down the mean field wave function for the chiral superfluid and then hitting it with the right long-range Jastrow factor. And it turns out that if you pick this correctly, you can open up a gap, but at the same time you can have this non-zero, this pattern of staggered currents in the system. So if you pick the Jastrow factor correctly, you can gap out the system, but you can still preserve this pattern of currents. So this sort of wave function with the right kind of Jastrow factor is a variational wave function for this chiral Mott state. Okay. So all this is fine. So the question is, what about experimental detection? Okay, I mean, so okay, fine. You might. This is probably a nice phase, but then how would you detect this experimentally? So once again, even though as we've sort of been discussing, maybe a lot of these experimental detections in cold atomic systems are a pipe dream, but the most concrete proposal that we can come up with is perhaps in the cold atomic physics context. So the idea is really, how do you detect staggered current? So it doesn't matter whether you're trying to detect the chiral superfluid or the chiral Mott insulator. How will you detect this any kind of chiral phase in a cold atoms context, let's say? So one idea is this, that if you have, let's say, such a staggered pattern of currents, so in this particular case, it's this vortex, anti-vortex, vortex, anti-vortex pattern. Let's assume that you have a square lattice, although I was talking about a bosonic ladder. Then it's a sort of checkerboard pattern. So how would you detect this? So one idea is that you actually use the fact that you can do dynamics and quenches in cold atom systems in a very systematic way to selectively switch off certain values of, to selectively switch off the hopping along some particular pattern of these bonds. Okay? So what is the idea? So you can see that in this particular staggered pattern, which is the equilibrium pattern, you have perfect current conservation at every site. So if you look at this site, you have as much current coming in as going out. Okay, and similarly this one. But let's say that I suddenly switched off the hopping along this particular bond. Then you'll see that here, where you have the yellow circle, you have more current coming in than going out, and where you have the blue circle, it's the other way around. You have more current going out than coming in. So this process of switching off the hopping would create some sort of charge imbalance. So if you could measure this, if you could measure the charge distribution after this sort of a quench in this system, which people are, I believe in principle, able to do, then the charge distribution that you measure can then be used to back out the original pattern of currents that existed. So this would be one way of looking for chiral ordering in these cold atom systems. And so this is a proposal from my collaborator Arun Paramakanti and one of his students. And as far as I can tell, this is perhaps at this point the most promising proposal. So let me just end by flashing this conclusion slide. So the main result of this work is that there is this chiral Mott insulator in this sort of frustrated bosonic system, which appears at intermediate values of interaction. And it's a Mott insulator with broken time reversal with this pattern of vortex and vortices and anti-vortices. And there's a physical picture for such a state in terms of a vortex, anti-vortex supersolid, and indirect excitonic condensate. And we can also write down a variational wave function. And it's possibly detectable in experiments on cold atom systems. Okay. Thank you. So, can I finish on time?
Questions?
Yeah.
Is there a simple intuition to what does the system gain from spontaneously breaking time reversal symmetry? Because it's a time reversal symmetric situation, right?
Right.
So what's the energetic gain from having this?
Yeah. So we can. So the superfluid phase. I mean, the simplest way to see that is that you have. So I had this Ginzburg-Landau type picture here. So you can write down some sort of Ginzburg-Landau type free energy, and the important thing is that you will have this Umklapp term here, which couples the order parameter at the k equal to 0 minimum and the k equal to pi minimum. And if you wanted to minimize this, so you can see that this is the only term which can actually change sign here. The only quartic term which can actually change sign. The others are all fixed to be positive. Mm-hmm. And you can see that this will change sign when the relative phase between k equal to 0 and k equal to pi is plus or minus pi by 2. So the energetic motivation for this sort of phase appearing is basically, at least within this sort of Ginzburg-Landau picture, this Umklapp term, which couples the two momenta.
Yeah.
Other questions? Krishnendu?
Yeah. One thing is, when you wrote down this term, I mean, is there a way to check if it is invariant under the symmetry group of the lattice? I mean, because there are two minima here now, one at 0 and another pi.
Right.
And when you combine these two to form this, this whole issue with this PSG thing that
Right. Yeah. So the short answer is, I haven't actually given much thought to that. The way this came about was you just start with your original, Bose-Hubbard Hamiltonian.
Yeah.
And then you write down, which is in real space, and then you write down write it down in momentum space and just look at what happens at a mean field level near the two minima. And then this is these are the quartic terms that you get.
Yeah, the rotation part might be a little tricky.
Right.
I don't know. I mean, and one small thing. So if I do this in 2D, with this thing, I mean, the Mott state is not quite featureless because if I look at the momentum distribution,
right, so you have precursor peaks. Well, exactly. So even here that happens.
So how is that related to the this Mott state here? Is it
Well, okay, so I should say that if you were calculating n of k, even here as a function of u, then what you would find is that, well, here this is a 1D system, so even...
But still, I mean,
right,
there...
Right. Yeah, I mean, you'd start seeing peaks, you'd have two peaks which will sort of eventually disappear in the Mott phase, and that's what's going to happen in 2D.
But that doesn't give you the signature of the transition, I guess.
Right, okay, so that doesn't, doesn't immediately tell you whether it's a crossover or whether it's a phase, right? You just see precursors, so that's, I guess, the prediction in your
I always
paper.
thought that it was a crossover,
Right.
Starts with
so it could well be a crossover in 2D. See, that's one of the reasons that we looked at this 1D system. Because, the thing is that at mean field level, there's only one transition. And if you believe that as you go up in dimension, you're going closer and closer to mean field, then, the chances of this phase existing in 2D are a lot smaller than existing in 1D. And in fact, I think Arun Paramakanti has been trying to do some simulations to look for this in 2D and so far hasn't been successful. So that's the reason we've looked at it in 1D.
Okay. Yeah, thanks.
Any other questions? If not, let's thank Subroto again.
Thank you.